nearby location, and aptly began shipping computers which had 32-bit clean ROMs beginning with the release of the 1989 Messiah. The 68,000 family stores multibyte integers in memory in big-endian order. Internal registers. The CPU has 8 32-bit general-purpose data registers, D0, D7, and 8 address registers, A0, A7. The last address register is the stack pointer, and assemblers accept the label SP as equivalent to A7. This was a good number of registers at the time in many ways. It was small enough to allow the 68000 to respond quickly to interrupts, even in the worst case where all 8 data registers D0, D7 and 7 address registers A0, A6 needed to be saved, 15 registers in total, and yet large enough to make most calculations fast, because they could be done entirely within the processor without keeping any partial results in memory. Note that an exception routine in supervisor mode can also save the user stack pointer A7, which would total 8 address registers. However, the dual stack pointer, A7 and supervisor mode A7, design of 68,000 makes this normally unnecessary, except when a task switch is performed in a multitasking system. Having the two types of registers allows one 32-bit address and one 16-bit data calculation to take place at one time. This results in reduced instruction execution time as addresses and data can be processed in parallel. 2. Status register. The 68,000 has a 16-bit status register. The upper 8 bits is the system byte, and modification of it is privileged. The lower 8 bits is the user byte, also known as the condition code register, CCR, and modification of it is not privileged. The 68,000 comparison, arithmetic, and logic operations modify condition codes to record their results for use by later conditional jumps. The condition code bits are 0, Z, carry, C, overflow, V, extend, X, and negative, N. The extend, X, flag deserves special mention, because it is separate from the carry flag. This permits the extra bit from arithmetic, logic, and shift operations to be separated from the carry for flow of control and linkage. Instruction set. The designers attempted to make the assembly language orthogonal. That is, instructions are divided into operations and address modes, and almost all address modes are available for almost all instructions. There are 56 instructions and a minimum instruction size of 16 bits. Many instructions and addressing modes are longer to include more address or mode bits. Privilege levels. The CPU, and later the whole family, implements 2 levels of privilege. User mode gives access to everything except privileged instructions such as interrupt level controls. 26. Supervisor privilege gives access to everything. An interrupt always becomes supervisory. The supervisor bit is stored in the state use register, and is visible to user programs. 26. An advantage of this system is that the supervisor level has a separate stack pointer. This permits a multitasking system to use very small stacks for tasks, because the designers do not have to allocate the memory required to hold the stack frames of a maximum stack up of interrupts. Interrupts. The CPU recognizes 7 interrupt levels. Levels 1 through 5 are strictly prioritized. That is, a higher numbered interrupt can always interrupt a lower numbered interrupt. In the status register, a privileged instruction allows setting the current minimum interrupt level, blocking lower or equal priority interrupts. For example, if the interrupt level in the status register is set to 3, higher levels from 4 to 7 can cause an exception. Level 7 is a level-triggered non-maskable interrupt, NMI. Level 1 can be interrupted by any higher level. Level 0 means no interrupt. The level is stored in the status register, and is visible to user-level programs. Hardware interrupts are signaled to the CPU using 3 inputs that encode the highest pending interrupt priority. A separate encoder is usually required to encode the interrupts, though for systems that do not require more than 3 hardware interrupts it is possible to connect the interrupt signals directly to theme-coded inputs at the cost of more software complexity. The interrupt controller can be as simple as a 74LS148 priority encoder, or may be part of a very large-scale integration, VLSI, peripheral chips such as MC68901 multifunction peripheral, used in the Atari ST range of computers, and Sharp X68000, which also provides a UART, timer, and parallel I/O. The exception table, interrupt vector table interrupt vector addresses, is fixed at addresses 0 through 1023, permitting 256 32-bit vectors. The first vector, reset, consists of 2 vectors, namely the starting stack address, and the starting code address. Vectors 3 through 15 are used to report various errors: buzzer or address error, illegal instruction, zero division, check and check 2 vector, privilege violation, to block privilege escalation, and some reserved vectors that became line 1010 emulator, line 1111 emulator, and hardware breakpoint. Vector 24 starts the real interrupts, spurious interrupt, no hardware acknowledgement, and level 1 through level 7 auto vectors, then the 16 trap vectors, then some more reserved vectors, then the user-defined vectors. Since the starting code address vector must always be valid on reset, systems commonly included some non-volatile memory, for example ROM, starting at address 0 to contain the vectors and bootstrap code. However, for a general-purpose system it is desirable for the operating system to be able to change their vectors at runtime. This was often accomplished by either pointing the vectors in ROM to a jump table in IAM, or through use of bank switching to allow the ROM to be replaced by RAM at runtime. The 68000 does not meet the Popek and Goldberg virtualization requirements for full processor virtualization because it has a single unprivileged instruction, move from SR, which allows user mode software read-only access to a small amount of privileged state. The 68EC000 and 68SEC000, which are later derivatives of the 68000, do meet the requirements as the move from SR instruction is privileged. The same change was introduced on the 68010 and later CPUs. The 68000 is also unable to easily support virtual memory, which requires the ability to trap and recover from a failed memory access. The 68000 does provide a bus error exception which can be used to trap, but it does not save enough processor state to resume the faulted instruction once the operating system has handled the exception. Several companies did succeed in making 68000-based Unix workstations with virtual memory that worked by using 2 68000 chips running in parallel on different phased clocks. Both leading 68000 encountered a bad memory access. Extra hardware would interrupt the main 68000 to prevent it from also encountering the bad memory access. This interrupt routine would handle the virtual memory functions and restart the leading 68000 in the correct state to continue properly synchronized operation when the main 68000 returned from the interrupt. These problems were fixed in the next major revision of the 68K architecture with the release of the MC68010. The bus error and address error exceptions push a large amount of internal state onto the supervisor stack in order to facilitate recovery, and the move from SR instruction was made privileged. A new unprivileged move from CCR instruction is provided for use in its place by user mode software. An operating system can trap and emulate user mode move from SR instructions if desired. Instruction set details. The standard addressing modes are register direct data register, for example D0. Address register, for example A0. Register indirect simple address, for example A0. Address with post increment, for example A0 plus. Address with predecrement, for example A0. Address with a 16-bit signed offset, for example 16, A0. Register indirect with index register and 8-bit signed offset, for example 8, A0 D0, or 8, A0 A1. Note that for A0 plus and A0, the actual increment or decrement value is dependent on the operand size. A byte access adjusts the address register by 1, a word by 2, and a long by 4. PC program counter, relative with displacement relative 16-bit signed offset, for example 16, PC. This mode was very useful for position-independent code. Relative with 8-bit signed offset with index, for example 8, PC D2. Absolute memory location, either a number, for example $4000, or a symbolic name translated by the assembler. Most 68,000 assemblers used the dollar symbol for hexadecimal, instead of 0x or a trailing H. There were 16 and 32-bit versions of this addressing mode. Immediate mode data stored in the instruction, for example #400. Quick immediate mode 3-bit unsigned, or 8-bit signed with MOVIC, with value stored in opcode. In ADCAN SUBC, 0 is the equivalent to 8. For example MOVIC #0D0 was quicker than CLR.LD0, though both made D0 equal to 0. Plus, access to the status register, and, in later models, other special registers. Most instructions have letter suffixes, permitting operations to occur on 8-bit bytes. B, 16-bit words. W, and 32-bit longs. L. Like many CPUs of its era, the cycle timing of some instructions varied depending on the source operand, S. For example, the unsigned multiply instruction takes 38 plus 2n clock cycles to complete, where n is equal to the number of bits set in the operand. 27. To create a function that took a fixed cycle count required the addition of extra code after the multiply instruction. This would typically consume extra cycles for each bit that wasn't set in the original multiplication operand. Most instructions are deduct. That is, the operation has a source and a destination, and the destination is changed. Notable instructions were arithmetic, add, sub, mulu, unsigned multiply, muls, signed multiply, divu, divs neg, additive negation, and CMP, a sort of comparison done by subtracting the argument sound setting the status bits, but did not store the result. Binary coded decimal arithmetic, ABCD, NBCD, and SBCD. Logic, EOR, exclusive OR, and NOT, logical NOT, or inclusive OR. Shifting, logical, i.e. right shifts put 0 in the most significant bit, LSL, LSR, arithmetic shifts, i.e. sign extend the most significant bit, ASR, ASL, rotates through extend and not, ROX, ROXA, ROL, ROR. Bit test and manipulation in memory or data register, set to 1, BCLR, clear to 0, BCHG, invert, and BTST, no change. All of these instructions first test the destination bit and set, clear. the CCRZ bit if the destination bit is 0, 1, respectively. Multiprocessing control, task, test and set, performed an indivisible bus operation, permitting semaphores to be used to synchronize several processors sharing a single memory. Flow of control, JMP, jump, JSR, jump to subroutine, BSR, relative address jump to subroutine, RTS, return from subroutine, RTE, return from exception, i.e. an interrupt, trap, trigger a software exception similar to software interrupt, check, a conditional software exception. Branch, BCC, where the CC specified one of 14 tests of the condition codes in the state use register, equal, greater than, less than, carry, and most combinations and logical inversions available from the status register. The remaining two possible conditions, always true and always false, have separate instruction mnemonics, BRA, branch always, and BSR, branch to subroutine. Decrement and branch, DBCC, where CC was as for the branch instructions, which provided the condition was false, decremented the low word of a deregister and, if the result was not -1, $FFFF, branched to a destination. This use of 1 instead of 0 as the terminating value allowed the easy coding of loops that had to do nothing if the count was 0 to start with no need for another check before entering the loop. This also facilitated nesting of 6080C000. Motorola 6080C000 controller. The 6080C000 is a low-cost version of the 68000 with a slightly different pinout, designed for embedded controller applications. The 6080C000 can have either an 8-bit or 16-bit data bus, switchable reset. 28. The processors are available in a variety of speeds including 8 and 16 MHz configurations, producing 2,100 and 4,376 dristones each. These processors have no floating point unit, and it is difficult to implement an FPU coprocessor, MC68881/2, with one because EVC series lacks necessary coprocessor instructions. The 6080C000 was used as a controller in many audio applications including Ensoniq musical instruments and sound cards, where it was part of the MIDI synthesizer. 29. On Ensoniq soundboards, the controller provided several advantages compared to competitors without a CPU on board. The processor allowed the board to be configured to perform various audio tasks such as MPU 401 MIDI synthesis or Mount 32 emulation, without the use of a terminate and stay resident program. This improved software compatibility, lowered CPU usage, and eliminated host system memory usage. The Motorola 6080C000 core was later used in the M68K-based Dragon Ball processors from Motorola /Freescale. It also was used as a sound controller in the Sega Saturn game console and as a controller for the PIET Direct Ethernet controller boards for the mid-1990s HP LaserJet printers. Example code. The 68000 assembly code below is for a subroutine named Statoloa, which copies a null terminated string of 8-bit characters to a destination string, converting all alphabetic characters to lowercase. 0010000 0010004E56000 001004306E0008 001008326E000C 0010000C1018 0010000E0C400041 00100126500 001001600C40050 0010001A62000006 0010001E06400020 001002212C0 001002466E6 001000264E5E 001000284E75 001000020 Statoloa. Copy a null terminated ASCII string, converting.